So this video is about isomers, particularly structural isomers. When we look at these two molecules, hopefully you can see they're clearly different. You have an oxygen that's double bonded to a carbon in this one, and in this one you have a carbon that's double bonded to another carbon. But when we look a little closer, we realize that they both share the same molecular formula. 4 carbons, 1 oxygen, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Also on this one, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So there's 8 hydrogens in both of them, 4 carbons, and 1 oxygen. They are structural isomers since they share the same molecular formula, but they have different connectivity. So let's take a look at one example in which you have C3H8. So you've got 3 carbons and 8 hydrogens, 3, 6, 7, 8. And you're asked, what other isomers can you make? The only way you can consider a new isomer is to take off one of the carbons, disconnect them, and then reconnect them in a new spot. Now, hopefully you realize reconnecting them to any of the other spots on this carbon is clearly going to make the same molecule. The only other thing is to put it to a new position. Now, if you do that, hopefully even that you might realize is going to pretty much make the same molecule again. You see, you connect it now to this carbon, and let's go ahead and reconnect the hydrogen to the other spot where you took it off, and now you have the same molecule. There is only one isomer for C3H8. So now let's take a look at C4H10. In this molecule, you have 4 carbons and 10 hydrogens. And I at least always recommend starting with the linear chain unless you have additional information, which is where all of this is heading. When you're in a lab or in real life, you can usually access many sources of information about your molecule or your unknown. Now, just right now today, or in this video, we're focusing on isomerism, structural isomerism again. And so what other isomers can we draw for this formula? As always, you start by disconnecting one of the carbons, or more. You can see, sometimes it'll be multiple groups of carbons, but I always start with one. And so that's like saying, let's take this group off here, and instead of placing it where we started it, let's place it someplace else. You still got most of what you had before, the 3 carbons, but we don't want to put it at the same spot here. We don't want to reconnect it here. That's where it started as. So let's try putting it some other spot. Let's try putting it here. So this is where we're going to take that group of methyls, putting it there in place of where the hydrogen was, and then going ahead and filling in all the rest of the hydrogens that we have. Now that's the same thing as taking what we did here, taking this off, and then taking it and placing it in the middle position of that 3 carbon chain. And then of course let's fill in where we left, the hole we left behind. And so now we have this molecule right here, which is clearly a new isomer than what we had before. It's not a linear chain. The next thing is, what if we connected it to the other side of the 3 carbons? So instead of, hopefully you realize if you just moved it to this position, it's the same thing. And I can do that for you right here. You take this off, place it where that hydrogen was, place the hydrogen where it was, and it's the same exact thing. So where else could we have placed it in this chain? So let's try placing it at the end, or one of these positions. Hopefully, once again, you realize putting it on any of these 3 is the same as each other. So you only have to pick one of them. It doesn't really matter. So let's just put it here and connect it in place of that hydrogen. So we're moving that methyl up here and just moving it over here. And then everything else gets filled in as before. So in doing that, we now have, it's as if we took this N carbon here, N hydrogen, excuse me, end of the carbon chain, excuse me, took the hydrogen that was there, replaced it with that methyl group, and then the hole that we left behind, in this case it was in the center because that's where we removed it from, we replaced with that hydrogen. And so hopefully you realize this is the same molecule as we had before. Maybe it was like this, I'm not really sure, I can't remember anymore, but it's still a straight chain of 4 carbons with hydrogens filling in the rest of the positions. This is the same as this one right here. Unfortunately, there's no easy answer to doing isomerism. It is essentially guess and check. And usually it's just on a sheet of paper. It's just expecting, hopefully, that you can do your 3-dimensional spatial visualization of what these molecules look like. Now, for examinations and lectures, usually we don't allow model kits. Can't really stop that with our open book examination, so I suppose you can do that. Now, when it comes to the lab, where you're going to be using this for the most part anyways, doing these unknowns, trying to figure out possible structures based on this as well as molecular formulas as well as additional information, you can use your model kit to kind of help you spatially visualize, are you drawing something new? This won't be the only thing, but it is a good starting point to draw isomers. Let's do one more. Let's start with C3H7Cl, and we'll start once again by drawing a chain of 3 carbons. Hydrogens always go last in my mind because they always just go where the carbon still needs bonds. And that's true as you get into more complex molecules and you are looking to find or place double bonds, rings, triple bonds, etc. Those degrees of unsaturation we talked about in the previous video, as well as these chlorine atoms. And so, or these other atoms, alcohols, OHs, etc. And so I usually put those first and then fill in the rest of the hydrogens. And so this is this molecule here. So what other isomers are there? Now you remember C3H8, there was only one. There was no other isomers, but because of this chlorine, this presents a piece of the molecule that we can remove and consider putting in another spot. Let's do like we did for the butane. Remove the hydrogen from the middle carbon of this 3-carbon chain and connect the chlorine to it, putting the hydrogen back where it was. We now do have a different molecule where the chlorine is now on the center carbon, and on the ends you have 2 essentially methyl groups, and then you have the other hydrogen. Very similar to butane, the C4H10, there really is no other isomer for this structure, because if you put the chlorine, if you replace the chlorine with this spot, you would not create a new constitutional isomer. Depending on what are in these positions, you might create a stereoisomer, as you may have learned already in Chapter 5. But you would not create a new structural or constitutional, as we call it, isomer, which is what we're really talking about right here. Same thing if you were to take the chlorine and put it on these hydrogens, just like we learned in the other example. But let's just show it once more. I'll replace it and replace it. Now it is on the other side. You might, oh, isn't that different? But than we had before. But I can just flip it around, and it's the same thing. And like I said, I can't remember. You can scroll back in the video if it was like this or like this, but it doesn't really matter. It was the same thing as putting it here. An example. Now, I'm going to show you that, at least for what we're watching this video for, which is spectroscopy and determining the structure of unknowns, you're usually given more information than just a molecular formula. So you're not going to just be drawing all the isomers of a structure. Usually you're given some information. Particularly the most helpful is the infrared spectroscopy that we're going to learn about more during experiment 3. Because of that, there will be part of the worksheet that won't be due until after that week of experimentation and the reading about infrared spectroscopy. And what the infrared spectroscopy typically tells us is things like this, that the molecule we're interested in has a C double bond O. And so now, when you do know that information in the formula, you're left to kind of considering all isomers that have a C double bond O of this formula. So that's really the skill we're trying to practice in this segment of the video. So you need 3 carbons still. And real quick, let's go ahead and do our degree of unsaturation calculation, which is going to be 2 times 3 plus 2 minus 6 over 2, because there's no nitrogens or halogens, which is going to be 6, 7, 8, 8 minus 6 divided by 2, which is 1. And since we are considering only molecules with a C double bond O, that double bond must be the unsaturation of this formula for what this problem or example is asking for. So let's not do any double bonded carbons. We're not going to do any rings either. So all the double bond is going to be is connected to one of these carbons as an connected between one of these carbons and an oxygen. And then once again, as I said earlier, fill in your hydrogens wherever there's still room. And then you don't even have to count them, except you should count them afterwards just to make sure. 1, 2, 3, 4, 5, 6. Just to make sure you didn't do something weird. We have 6 hydrogens. It should always work out as long as you're considering the correct number of bonds that carbons typically require and your bonding to oxygen is correct. So that's one isomer. And what we're going to do is since we know we have to have a C double bond O, we're going to do like we did in the earlier examples for just basic isomerism, is just move a unit around. In this case, we're going to move the double bond O around. And so I'm going to move this double bond O over to this carbon. And so that's going to give me C double bond O in the center. Oops, there's nothing there. That's already got 4 bonds. So this then has H, 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 H. So that is another isomer. You could move it over one more carbon, but hopefully by now you realize just doing that, you're going to end up with a structure that looks like the reverse of this, and it's the same molecule. Now, if this was a longer chain or had maybe halogens in it, you would need to consider moving those around. That would lead to more isomers. So you always have to consider, is there other things that I can move around in these two structures that I've drawn based on moving this first thing, the C double bond O, around? If there was maybe, let's say, a chlorine in these, for example, here, then I would need to consider what would happen if I move this chlorine for this arrangement of carbon and oxygen to this position. Is that a new isomer? In this case, it would not be, because this molecule is symmetric. So whether you put the chlorine here, 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 you would always have the same molecule. I challenge you at home to maybe build the model kit and test it for yourself. Now, if we had a chlorine in this structure, there are some other possibilities. The chlorine could be on this carbon. In either of these positions, it would be the same isomer, structural isomer, or it could be on this carbon, and that would be a different isomer, putting it on this carbon. Whether you put it here, here, or here isn't really going to affect the structural or constitutional, as we call it, isomer. It would be the same, regardless of where you put it. And it would look like this. And then also, another one you would have is what if you put the chlorine here? So what we've done, just so you're not confused, the first two structures I drew without a chlorine, where they were just hydrogens, that was the original problem that I gave, which is draw all the isomers of C3H6 The thing that I kind of shifted into was the idea that when you introduce maybe an additional piece to the molecule, like a chlorine atom, maybe another oxygen atom, maybe as like an alcohol group, or even a longer chain of carbons, you can break those down and move them around, very similar to the earlier examples I gave for finding different isomers for, say, C4H10, where we were moving methyl groups around and moving the carbon pieces to different connections. You can do the same thing when you've drawn out a series of isomers by moving some other part of the molecule. You can move on to some other unit to draw further new isomers, like I did, assuming there was a chlorine involved in these molecules. So that's the example. Go ahead and we're going to move on to the next part of this topic. And then eventually, during our week of NMR, we will be practicing this in our worksheet.